What if we found a habitable planet tomorrow? At 6:42 in the morning, Dr. Leona Reyes is standing behind a curtain in a windowless conference hall, listening to the sound of 300 journalists taking their seats. On the other side of the curtain, a screen displays a single point of light. The point is visible not because the planet is large or bright, but because several observatories have spent years learning how to separate its faint reflected light from the glare of the star beside it. The star is 12.3 light-years from Earth, close enough to be one of the Sun's neighbors, and still more distant than any human journey has ever attempted. The planet has an official designation that sounds like a filing code: Hesper 417c. For the moment, that is all the public knows. Leona looks down at the first sentence printed on the card in her hand. She has rewritten it 11 times. Every version sounded either too cautious for the importance of the discovery or too dramatic for the limits of the evidence. The curtain opens. Cameras turn toward the stage. Leona walks to the lectern and says that an international team has confirmed a rocky planet with stable surface temperatures, a substantial atmosphere, and persistent liquid water. For several seconds, the room remains perfectly quiet. Then everyone begins speaking at once. The news alerts appear before Leona reaches the second paragraph. Habitable planet confirmed. Possible second Earth discovered nearby. New world may contain oceans. Humanity finds another home. The final headline is the one she feared most. Astronomers find planet humans could live on. She has not said that. She will spend the rest of the morning explaining why. A habitable planet is not necessarily a human-safe planet. In astronomy, habitability usually begins with a more modest question. Could environmental conditions allow liquid water and some form of life, at least somewhere on the world, for a meaningful period of time? The term does not promise breathable air. It does not promise edible plants, harmless microbes, gentle weather, familiar gravity, or a surface where an unprotected person could stand. Mars was once more habitable than it is now and may still contain environments suitable for microorganisms below the surface. Nobody would call present-day Mars comfortable for a human body. Earth itself has been habitable for life across billions of years, during which a modern human would have suffocated in its atmosphere. So tonight's thought experiment needs one careful rule. Tomorrow's discovery is stronger than finding an Earth-sized planet at the right distance from its star. Astronomers have already found rocky worlds and habitable zones, but orbit alone cannot reveal whether liquid oceans actually exist. A planet may lie in the right region and still resemble Venus, Mars, or something entirely unfamiliar. In the real world today, no operating telescope could confirm oceans, seasonal ice, atmospheric pressure, and surface habitability on an Earth-sized exoplanet with the confidence used in this story. The next generation of direct imaging observatories is being designed for exactly that kind of work. So our thought experiment grants astronomy one additional step. An experimental network has achieved capabilities slightly beyond current instruments. The announcement comes tomorrow, but the observing technology is a little ahead of ours. With that condition established, several independent methods agree. The planet is slightly larger than Earth and has a measured mass consistent with a rocky composition. It circles a quiet orange K-type star in a stable orbit lasting 281 Earth days. Repeated observations reveal an atmosphere dominated by nitrogen, with water vapor, carbon dioxide, clouds, and a significant but not yet fully explained amount of oxygen. Patterns in reflected light show broad dark and bright regions changing as the world rotates. Polarization measurements are consistent with large bodies of liquid water. Seasonal changes suggest ice expands and retreats near the poles. Climate models using the observed atmosphere produce surface temperatures that could allow oceans, rainfall, and temperate regions. No single measurement would be enough. Together, after years of observation and independent checking, They create the first case strong enough for scientific institutions to use the word habitable without placing potentially in front of it. The discovery still does not prove life exists there. Oxygen can be produced by living organisms, as it is on modern Earth, but under some conditions it can also accumulate through non-biological chemistry. Water is necessary for all known life and is not evidence that life began. Clouds can move over a sterile ocean. Seasons can change on a world where nothing has ever been alive. The planet is habitable. Whether it is inhabited remains unknown. That distinction becomes the center of everything that follows. The announcement feels sudden to the public, but nothing about the science was sudden. The first hint appeared 7 years earlier as a tiny periodic shift in the spectrum of Hesper 417. The star moved toward Earth and away again by less than the speed of a person walking. That motion suggested an orbiting planet pulling the star through gravity. A second observatory detected the same rhythm. The planet did not pass directly in front of the star from Earth's point of view, so astronomers could not use an ordinary transit to measure its atmosphere. Instead, the team relied on direct imaging, interferometry, precise radial velocity measurements, and years of observations made at different points in the orbit. Seeing an Earth-sized planet beside its star is like trying to photograph a firefly beside a lighthouse from thousands of kilometers away. The star is billions of times brighter at visible wavelengths. Instruments must suppress the starlight without removing the planet's faint signal. The first images showed only a few pixels. Those pixels contained a spectrum. Different molecules absorb and reflect different wavelengths of light. By separating the planet's light into its component colors, astronomers identified water vapor, carbon dioxide, oxygen, and the broad influence of clouds. By observing across the orbit, they watched the brightness and spectrum change. A glint appeared at certain angles. On Earth, sunlight reflecting from oceans can create a similar directional signal. The team tested whether clouds, ice, minerals, or instrumental effects could imitate it. Some could reproduce parts. None reproduced every observation. The scientists did not call a press conference. They collected another year of data. The atmospheric models produced a troubling result. The apparent oxygen concentration seemed high enough to attract claims of life, but the star's ultraviolet radiation might split water molecules and allow hydrogen to escape, leaving oxygen behind without biology. The team studied the star. It was older and quieter than many red dwarfs, with fewer powerful flares. The measured water abundance and carbon monoxide placed limits on several false positive scenarios. The oxygen remained interesting. Still, the scientists did not call a press conference. They invited independent teams to analyze copies of the data without being shown the original interpretation. One group found the same atmospheric molecules. Another challenged the ocean glint result. A third discovered a small calibration error that reduced confidence in the first seasonal map. The public heard rumors. An astronomer posted a photograph of champagne bottles in a laboratory refrigerator. A telescope schedule showed unusually long observations of one nearby star. An online forum identified Hesper 417 as the likely target. The institution refused to comment. Leona disliked the secrecy, but she understood the danger of announcing the most important exoplanet result in history before understanding whether a warm detector or an uncorrected mirror vibration had created part of it. Extraordinary discoveries do not require extraordinary evidence because scientists enjoy delay. They require it because human beings are skilled at seeing what they hope to find. The team observed the planet through another full orbit. Ocean-like reflection returned at the predicted phase. Cloud patterns changed. The polar signal strengthened during one season and weakened during another. A separate instrument detected the same water and oxygen features through a different technique. Only then did the institutions prepare the announcement. Leona reaches this history during the press conference, but the questions have already moved ahead. Is there life? Can humans breathe there? How soon can we go? Who owns it? Could intelligent beings be watching Earth? Leona answers each question with some version of not yet, probably not, or we do not know. The journalists are not disappointed. Uncertainty makes the room louder. Outside the conference hall, the discovery spreads across the planet faster than any spacecraft ever could. In Madrid, commuters watch the press conference on trains. In Nairobi, students gather around a classroom screen. In Seoul, an electronics market turns every television toward the same pale image. In rural towns where the star cannot be seen in the daytime, people step outside anyway and look upward. The planet is not visible without specialized equipment. Even its host star is too faint for most unaided eyes. That does not stop anyone from trying. At home, Leona's 11-year-old daughter, Mara, is watching with her grandfather. Mara knows her mother helped make the discovery, but until this morning, she believed the secret project involved atmospheric calibration. When Leona says the word stable liquid water, Mara begins crying. Her grandfather asks whether she is frightened. Mara says no. She is angry that the planet existed every day of her life and nobody had told her. Her grandfather explains that nobody knew. Mara looks at the screen and says the planet knew. It had been orbiting its star for billions of years without waiting for human confirmation. By noon, that sentence has already become true in another sense. The discovery has changed humanity's knowledge. It has changed nothing at Hesper 417c. The first day belongs to headlines. The first week belongs to correction. News organizations quickly learn that every attractive word carries a scientific trap. Earth-like may refer only to size. Temperate may describe the amount of energy received from a star rather than the weather on the ground. Oxygen may be biological or geological. Liquid water may cover an ocean, exist beneath clouds, or survive only in certain regions and seasons. A planet can be habitable without being comfortable. A planet can be comfortable without being alive. A planet can be alive without being safe for human beings. Leona repeats these distinctions until they begin appearing in public broadcasts without her. The official image of Hesper 417c shows a blue-gray sphere with pale clouds and a darker ocean. It is not a photograph in the ordinary sense. The planet occupies only a handful of resolved elements in the best observations. The image combines measured brightness, spectral data, rotation, climate modeling, and artistic reconstruction. A label beneath it states that the surface appearance is scientifically informed but not directly photographed in this detail. The label is removed whenever the image circulates online. Within hours, people are sharing beaches, forests, mountains, and cities that no telescope has seen. Some images show violet vegetation beneath an orange sun. Others show an untouched Earth waiting for settlement. One popular version contains 2 moons, although no moon has been detected. The false images do not remain harmless decoration. A financial company announces a fund investing in future Hesper industries. A property website offers symbolic land certificates on the planet. A spiritual teacher claims to have received messages from its inhabitants. A political commentator says the discovery proves environmental protection on Earth is unnecessary because humanity now has a backup. Every claim moves farther from the evidence while using the authority of the original announcement. The scientific institutions establish a public data center within 48 hours. Raw observations, calibration methods, atmospheric models, and uncertainty ranges are released as quickly as legal and technical review allows. Independent researchers begin checking every result. This does not end misinformation. It makes correction possible. Mara watches her mother answer questions late into the night. Leona has slept only 3 hours since the announcement. She is not responsible for every misunderstanding on Earth, but each one feels connected to a sentence she might have explained better. Her father, Tomás Reyes, tells her to stop watching. Tomás was a school physics teacher for 38 years. He knows the difference between explaining and controlling whether someone understands. He brings Leona a bowl of soup and asks the question nobody asked at the press conference. What does the planet look like right now? Leona answers that they do not know. The light arriving from Hesper 417c left 12.3 years earlier. The world being celebrated this morning is the world as it existed more than 12 years ago. If a storm is crossing its ocean now, Earth will not see it until the light arrives in the future. If a volcano has erupted, if an ice sheet has changed, or if a civilization has appeared, vanished, or sent a signal, that information is still traveling. Astronomy turns distance into history. The planet is nearby by galactic standards and permanently delayed in human experience. This delay shapes the first serious debate about communication. Radio observatories begin listening toward Hesper 417 before the press conference ends. They search narrow frequency bands for artificial-looking signals. Optical telescopes search for unusually brief laser pulses. Infrared observations look for waste heat or structures that might suggest large-scale technology. Nothing is detected. This tells astronomers very little. A civilization may not exist. It may not use radio. It may transmit in directions that never cross Earth. Its technology may be too weak, too unfamiliar, or too old. It may have lived during a period whose signals passed Earth centuries ago. It may be present now while the light currently reaching Earth shows an earlier time. Silence from one day of listening is not evidence of an empty world. A private organization announces plans to transmit a message. Its proposed broadcast contains mathematics, basic chemistry, human anatomy, music, and a map locating the solar system. Supporters call it a greeting. Critics call it a decision made on behalf of billions of people who were never consulted. The message would take 12.3 years to arrive. Any reply would require at least another 12.3. A child born on announcement day would be almost 25 before the earliest possible answer reached Earth, assuming recipients detected the message immediately, understood it, chose to respond, and possessed compatible technology. The debate therefore feels both urgent and unreal. Nothing sent tonight can produce an immediate consequence. Everything sent tonight may become the inheritance of people who had no role in the choice. Governments ask major transmitters to pause deliberate messaging while international consultations begin. The request is voluntary in several countries and legally uncertain in others. A sufficiently powerful, focused transmission requires substantial equipment, but the principle is difficult to contain. Who has the right to speak for Earth? A national government? The scientific team that discovered the planet? The United Nations? Every person through a global vote? Nobody, until evidence of intelligence appears. The question has existed in quieter form for decades. A confirmed habitable target gives it coordinates. Leona is invited to the first international meeting on communication. She does not want to attend. She studies atmospheres, not diplomacy. Her name is attached to the discovery, which means people assume she possesses authority over every consequence. At the meeting, one participant argues that Earth has already been leaking radio signals into space for more than a century. Another explains that ordinary leakage becomes weak and difficult to detect across interstellar distance, while a focused high-power transmission would be different. A philosopher asks whether silence is itself a message. A security advisor asks whether a civilization capable of harming Earth would need humanity to announce its existence. An astronomer points out that if they can resolve Earth as well as Earth resolves their planet, they may already know oxygen, water, and industrial gases are present here. Nobody reaches agreement. A temporary protocol recommends no official reply because no intelligent signal has been detected. Listening expands. Deliberate transmission remains politically disputed. The first week also brings religious responses, though not the uniform crisis predicted by some commentators. Many traditions have considered worlds beyond Earth long before the discovery. Religious leaders describe the planet as another part of creation. Some congregations hold nights of observation. Scholars revisit old texts and philosophical arguments about whether life, intelligence, or moral responsibility might exist elsewhere. Other communities react with discomfort. A few leaders reject the announcement. Others accept the planet while resisting any suggestion that it diminishes human significance. Most believers continue their ordinary lives. The planet does not answer questions about God, purpose, or morality merely by possessing an ocean. It changes the scale on which those questions can be asked. Philosophers receive more interview requests than at any time in recent memory. They discuss whether human importance depends on uniqueness. Some argue that discovering another habitable world reduces the idea that Earth occupies a special position. Others say rarity and value are not the same. There are billions of human beings. A particular person can still be irreplaceable. A second habitable planet would not make Earth disposable any more than the existence of another forest makes one forest meaningless. Environmental organizations use the discovery in opposite ways. One campaign places the two planets beside each other with the words habitable is rare. Another uses the measured distance. The nearest confirmed alternative is 12.3 years away at the speed of light and far longer by spacecraft. There is no planet B within reach. The slogan is not entirely new. The number makes it physical. Markets react strongly for several days. Telescope manufacturers, aerospace firms, satellite companies, and speculative propulsion ventures rise. Companies with no relevant technology add interstellar to their names. Scams offer shares in future mines and migration projects. The excitement fades when investors understand the distance. No mineral from Hesper 417c can return on a useful commercial timescale. No hotel can open there. No current rocket can carry a human within anything resembling a lifetime. The planet may transform science. It will not become real estate tomorrow. Public interest does not disappear with the first correction. Schools organize viewing events even though the planet cannot be seen through ordinary telescopes. Planetariums add emergency programs. Museums print the spectrum at enormous scale and show visitors where water, oxygen, and carbon dioxide leave their signatures. Children ask direct questions. Does it rain there? Are there fish? What color is the grass? Could a person catch a cold? Would alien life use DNA? Scientists answer that none of these questions can yet be answered. Children are often more comfortable with that than adults. Mara's school invites Leona to speak. Mara sits in the back, pretending not to know her. A student asks whether the planet has a name. Leona explains that Hesper 417c is a catalog designation. Hesper 417 is the star. The letter C means it is the second planet discovered in the system, not the third planet from the star. The student says the name sounds like a printer. The room agrees. By the end of the week, an international naming campaign has already received more than 40 million suggestions. The most popular include Haven, Gaia, Eden, Aurora, Hope, and Home. Leona dislikes all of them. Each name assumes an answer. A planet humanity has never touched should not be named as though it has already been assigned a purpose. The naming campaign lasts 6 months and produces exactly the kind of conflict Leona expected. Every proposed name carries history. Eden belongs to religious traditions and implies a garden before anyone has seen land. Gaia is already tied closely to Earth. Haven suggests safety. Hope describes a human emotion rather than the planet. Names drawn from indigenous languages attract support and concern about removing words from their cultural context. Some astronomers want to keep Hesper 417c permanently. Catalog names are clumsy, but they do not pretend possession. Mara suggests Nila, a word associated with blue in several languages and names, because the planet appears to contain oceans, but blue does not claim it is friendly. Leona points out that the color is still partly reconstructed. Mara says every name is partly reconstructed. The final global vote chooses Pelagos from an old word for open sea. The name is not universal and does not replace the scientific designation. Some languages adapt it. Many people continue saying Hesper Sea. The planet now has a name people can remember. This changes public emotion more than any new measurement. Pelagos begins appearing in poems, songs, clothing, political speeches, and children's books. A planet that existed as a spectrum becomes a place in imagination. People draw coastlines the data cannot resolve and fill oceans with creatures no instrument has detected. Scientists resist and participate at the same time. They know artist impressions can be mistaken for evidence. They also know the human mind struggles to care about a table of wavelengths. The official visualization team releases several versions labeled by certainty. One shows only the measured light and the broadest possible surface map. One shows a conservative climate reconstruction. One shows several scientifically plausible appearances, a mostly ocean-covered world, a world with large continents, and a cloudier planet where much of the surface remains hidden. The range becomes part of the story. Pelagos may be familiar in broad physics and alien in every detail. During the first year, telescope time becomes the most contested scientific resource on Earth. Thousands of research groups submit proposals. Atmospheric chemists want better measurements of oxygen, methane, carbon monoxide, and water. Climate scientists want cloud maps and seasonal changes. Geologists search for volcanic gases and mineral signatures. Astronomers monitor the stars' ultraviolet and X-ray output. SETI teams listen for technology. Every observation taken of Pelagos is an observation not taken of another target. Some researchers worry that one famous planet will consume the field. More than 6,000 exoplanets are already confirmed, and thousands of candidates remain. The galaxy cannot be understood through one unusually attractive world. Funding agencies increase budgets rather than solving the problem by selection alone. New instruments are proposed within weeks. Some are realistic extensions of existing designs. Others promise impossible detail and attach Pelagos to old ideas in search of money. The discovery gives every project a destination. A large space telescope already in development is redesigned to improve direct imaging at the separation between Pelagos and its star. Engineers study whether a separate star-shade spacecraft could fly tens of thousands of kilometers from the telescope and block the star with enough precision to expose the planet more clearly. Ground-based observatories combine light across multiple telescopes. Their enormous mirrors and adaptive optics fight atmospheric distortion. Radio arrays dedicate repeated sessions to the Hesper system. No one instrument can answer everything. The next picture emerges through combination. Pelagos rotates once every 31 hours. The estimate comes from repeating changes in brightness as oceans, clouds, and land-like regions turn in and out of view. Its axial tilt appears moderate. Seasons exist, though they are not identical to Earth's because the orbit and atmospheric circulation differ. The planet may contain two major ocean basins separated by broad land masses. The map is extremely coarse, more like recognizing continents in a blurred reflection than seeing coastlines. Clouds gather repeatedly near one equatorial region. Climate models suggest persistent convection and heavy rainfall. A drier subtropical band may contain desert or open rock. A large bright area near the northern pole changes with season, consistent with water ice. Each discovery produces another illustration. Each illustration feels more detailed than the evidence. Leona becomes cautious about looking at them. The image in her imagination begins competing with the planet in the data. She teaches Mara to read spectra instead. They sit together at the kitchen table with colored graphs. Leona shows how absorption lines identify gases and how uncertainty appears as shaded regions. Mara prefers the clouds. She asks whether oxygen means trees. Leona explains that Earth's oxygen was produced first by microscopic organisms, long before forests. Photosynthesis could evolve differently elsewhere. A planet may have abundant life without anything resembling a plant. Mara asks whether life there would be green. Light from the orange star contains a different balance of wavelengths than sunlight. Photosynthetic organisms might use darker pigments to absorb more available energy. They might appear purple, black, red, or something human eyes do not categorize easily. The answer excites Mara more than trees would have. She begins drawing black forests beneath a copper sky. The second year brings the first apparent biosignature crisis. A research team reports a weak methane signal in the atmosphere. On Earth, methane and oxygen react and cannot remain together for long without continuous replenishment. Life produces much of Earth's methane, though geological processes produce some. Oxygen plus methane in strong chemical disequilibrium could be more suggestive than either gas alone. The paper is released before every team agrees. Headlines announce life. Markets surge again. Religious services fill. Crowds gather outside observatories. A private organization schedules a transmission ceremony. Leona reads the analysis and feels the old excitement rise despite herself. The methane feature appears in several observations. It also overlaps with an instrumental effect and a molecule in Earth's own atmosphere that ground-based telescopes must remove from the data. Independent teams cannot reproduce the strength of the signal. For 3 weeks, the world lives between life and calibration. The final result is frustratingly balanced. Methane may be present, but the concentration is below confident detection. The evidence is not strong enough to claim atmospheric disequilibrium. Scientists call it unresolved. Many people call it a cover-up. The episode damages trust, especially because several institutions communicated with different levels of confidence. One press release said tentative. Another said possible sign of life. A headline turned possible into likely. Leona appears at a public hearing and explains that science did not reverse a fact. It improved an uncertain measurement. The distinction is difficult to accept after hope has already become certainty. Mara, now 13, is angry with the team that published early. Leona asks whether researchers should hide interesting results until they become certain. Mara says no. Leona asks whether they should avoid discussing uncertainty because people may misunderstand. Mara says no again. They sit with the problem. Open science allows errors to be found. Premature certainty allows errors to become public memory. The institutions create a shared evidence scale for future announcements. Atmospheric features receive confidence levels. Potential biosignatures must include known non-biological explanations. Major releases are coordinated without giving one team the power to silence disagreement. The system cannot prevent every sensational headline. It gives careful readers a map of confidence. The methane crisis also changes how people understand discovery. Finding another living world will probably not happen through one perfect image of an alien animal. It may begin as an imbalance in gases, repeated across instruments, and argued over for years. Life may enter human knowledge as a probability before it enters as a fact. This is uncomfortable. People want a door that is either open or closed. The universe often provides a hinge moving slowly. Scientific work continues beneath the public drama. Spectroscopy narrows the oxygen abundance. Climate models become more stable. The planet's atmospheric pressure appears between roughly 3/4 and 1.5 times Earth's sea level pressure, though the range remains wide. This matters for liquid water and climate. It does not establish breathability. An atmosphere containing oxygen can also contain toxic gases. Pressure can vary with altitude. Aerosols, microbes, dust, and chemistry at the surface remain unknown. Human lungs evolved for Earth's particular mixture and history. Even if a future probe confirmed air with the right oxygen concentration and no obvious poison, stepping outside would be irresponsible. Alien biology, if present, might interact with human cells unpredictably. Earth microbes could damage Pelagos in return. The phrase second Earth slowly loses favor among scientists. Pelagos is not Earth twice. It is the first Pelagos. This correction enters Mara's life more deeply than she expects. At school, classmates know her as the daughter of the woman who found the planet. Some assume she will become an astronomer. Others ask for secret information she does not have. Teachers choose her for space projects. Mara begins refusing. She studies marine biology instead. Leona recognizes the rebellion and does not interfere. Pelagos may have oceans. Mara wants to understand the one beneath Earth's sky first. By the third year, Pelagos has become ordinary enough to enter politics. Candidates place it in speeches about science, destiny, climate, education, national strength, and human unity. One leader promises to make their country the first to reach the new world. The promise receives applause despite the absence of any spacecraft capable of crossing the distance within a human lifetime. Another politician calls the planet a distraction invented by elites while people struggle on Earth. Both statements simplify the same reality. Pelagos is scientifically important and practically unreachable. It deserves study and cannot solve tomorrow's housing, hunger, conflict, or climate. The discovery makes arguments about Earth's environment more vivid. Climate researchers compare the two planets carefully, not because Pelagos provides a replacement, but because it offers a second example of a temperate atmosphere. Earth science had long relied on comparisons with Venus, Mars, and other planets. Venus shows how a dense carbon dioxide atmosphere can create extreme greenhouse warming. Mars shows how a small world can lose much of its atmosphere and surface water. Pelagos adds another climate system built from similar ingredients under a different star. Observations suggest its clouds reflect a larger fraction of incoming light than Earth's. Its oceans may transport heat efficiently. A somewhat denser atmosphere could moderate temperature differences between day and night. These findings improve planetary climate models. They do not provide a formula for repairing Earth's climate. The star is different. The continents are different. The atmosphere has a different history. The planet may contain life that altered its chemistry in unknown ways. Still, Pelagos becomes a mirror in public imagination. An image from the first announcement appears at a global climate summit beside a photograph of Earth. The caption reads, "One is home. One is 12 light years away." Environmental groups use the distance to challenge escape fantasies. Even a spacecraft traveling 1,000 times faster than today's fastest interplanetary probes would require thousands of years to reach the planet. Pelagos is not an evacuation site for any present crisis. Companies selling symbolic migration places disappear after regulators intervene. The scientific comparison produces a more useful lesson. Habitability is not a permanent label. Earth's atmosphere, oceans, climate, and life have changed repeatedly. Pelagos is being observed during one brief slice of its history, delayed by 12 years. Its star will evolve. Its geology may alter atmospheric gases. Oceans can freeze or evaporate. Life, if present, can transform a world. A habitable planet can become uninhabitable. A hostile planet may once have been mild. The discovery makes planetary stability feel less like a possession and more like a continuing process. Mars programs continue. For several months, Commentators ask whether a distant world with oceans makes the dry red planet irrelevant. Engineers answer that Mars is reachable within months, can teach humans to live beyond Earth, and remains scientifically valuable regardless of any exoplanet. Pelagos and Mars occupy different futures. Mars is a difficult neighboring world that machines can visit now and humans may visit within decades. Pelagos is a possible living world whose light can be studied now and whose surface may remain physically untouched for generations. One does not replace the other. The Moon remains important for the same reason. Telescopes on or near the Moon's far side could observe radio frequencies protected from Earth's noise. Lunar industry might support larger space instruments. Technologies developed for Mars, the Moon, asteroids, and deep space missions could eventually contribute to interstellar probes. The discovery creates a ladder rather than a leap. Nearer missions build skills needed for farther ones. Governments and private organizations compete to define the next step. The most persuasive proposal does not contain people. It contains a wafer of electronics, a camera, a laser communication system, and a sail thinner than paper. Dr. Soren Malik presents the concept at an international engineering meeting. He is a propulsion physicist who has spent years studying laser-driven light sails. The idea existed before Pelagos. Use a powerful array of lasers to accelerate extremely small spacecraft to a significant fraction of the speed of light. A conventional rocket carries fuel and must accelerate its own fuel. A light sail receives energy from far away during the initial push. If the sail and payload are light enough, a sufficiently powerful laser array could accelerate them far beyond the speed of any current probe. The physics does not violate relativity. The engineering approaches the edge of imagination. The laser array would require enormous power, exquisite coordination, and optics capable of focusing across great distance. The sail must survive acceleration, heat, dust impacts, and decades in interstellar space. The probe must navigate without repair, awaken at the target, collect useful data during a rapid flyby, and send a signal back with a transmitter small enough to ride on the sail. At 20% of the speed of light, the journey to Pelagos would take a little more than 60 years. The data would then require another 12.3 years to reach Earth. A probe launched 15 years after discovery might deliver results roughly 88 years after the press conference. Leona would not live to see them. Mara might not. The timeline does not weaken public interest as much as Soren expected. It changes the kind of interest. The Pelagos probe initiative is designed from the beginning as a multi-generational institution. Its founding documents do not describe a project team that will finish a mission. They describe a chain of custody extending across careers and lives. Every system must be understandable to engineers not yet born. Every decision must be documented for people who cannot ask the original designer what was intended. The mission becomes partly an exercise in technological humility. Present engineers can build the launch system. Future engineers will inherit its consequences and may possess better ideas. The first proposal calls for one probe. Reviewers reject it. At interstellar distance, there is no repair mission. A grain of dust can destroy a vehicle traveling at a fraction of light speed. Electronics can fail. Navigation can drift. A single probe creates one point of failure. The revised mission sends hundreds of small probes in waves. Most carry similar core instruments. Some specialize in imaging, magnetic fields, plasma, dust, or spectroscopy. A few separate near the destination to observe the star, other planets, and Pelagos from different angles. Redundancy increases cost and creates a scientific network instead of one heroic machine. The public names the fleet Fireflies. Soren dislikes the name until Mara sends him a drawing of tiny lights crossing a dark page toward a larger blue point. She is 16 by then and has never met him. Soren keeps the drawing above his desk for the next 40 years. The probe initiative creates immediate technology even though arrival lies far away. Laser control improves. Lightweight materials advance. Autonomous navigation becomes more capable. Space-based power systems receive investment. Precision clocks and miniature sensors improve. Some benefits spread into medicine, communications, climate monitoring, and Earth observation. Others remain useful only to an extraordinary mission. Critics ask whether billions should be spent on data that current taxpayers will never receive. Supporters answer that many societies build institutions, archives, forests, cathedrals, and scientific projects whose benefits extend beyond one generation. A democratic society must still decide how much future knowledge is worth compared with present need. The mission survives by refusing to present itself as the only worthy project. Its budget grows slowly. It shares technology with Earth science and planetary missions. International partners contribute instruments, power infrastructure, and tracking stations. No country owns the fleet. That last principle becomes difficult when competition returns. Two nations announce separate high-speed probe concepts with more aggressive timelines. One promises a launch within 8 years, using technology not yet demonstrated. Another insists that the first close image of Pelagos should be a national achievement. Soren tells a government committee that speed can destroy the mission before it leaves. A sail pushed too hard may deform. A rushed fleet may carry instruments that cannot survive. An underpowered communication system could reach the planet and return silence. Interstellar travel punishes optimism that is not converted into engineering margin. The independent projects continue. Competition accelerates useful work and duplicates expensive mistakes. Cooperation and rivalry grow together, as they have throughout the history of spaceflight. Pelagos has not united humanity. It has given humanity a shared direction in which to compete. Human travel remains a different category of problem. A crewed ship cannot be reduced to a camera and a processor. It must protect living bodies from radiation, provide food, water, air, gravity or exercise, medicine, spare parts, and social stability across decades or centuries. It must slow down at the destination rather than pass through the system in hours. A generation ship would turn the journey into a society. Children born aboard would inherit a destination chosen before their birth. They might reach Pelagos without having consented to leave Earth. The ship would need laws, education, population planning, conflict resolution, and an ecosystem reliable enough to operate longer than any sealed habitat ever built. If the planet contains life, arrival creates another problem. The travelers may have crossed 12 light years only to discover that landing is ethically unacceptable. A living world cannot be treated as vacant because no cities are visible. Settlers would need orbital habitats, artificial worlds, or a different destination while studying the biosphere from distance. Suspended animation is proposed as an alternative, but no current method can place healthy humans into safe hibernation for an interstellar voyage. Faster propulsion may reduce travel time, yet the energy required rises enormously as speed increases. Dust that seems harmless at ordinary velocity becomes dangerous at a significant fraction of light speed. These obstacles do not prove human arrival will remain impossible forever. They explain why a confirmed habitable planet would not produce an immediate migration program. The first serious physical mission would almost certainly be robotic. Human travel would require breakthroughs in propulsion, closed ecosystems, radiation protection, medicine, governance, and planetary ethics at the same time. Pelagos would give those questions a real destination. It would not make them solved. The question of communication does not remain politely theoretical. 7 years after the discovery, an observatory detects a narrow radio signal from the direction of Hesper 417. The signal lasts 43 seconds. It appears near a frequency used in many searches because natural cosmic sources rarely produce such narrow emission. It drifts in a way that could be consistent with a transmitter on a rotating, orbiting world. The detection occurs during a maintenance test and is recorded by 2 instruments at the same facility. Within minutes, the observatory contacts other radio telescopes. Within an hour, someone posts a screenshot. The screenshot contains no context, but the word candidate is visible. By sunrise, millions of people believe Pelagos has answered. The signal does not repeat. Other observatories search the same frequencies and find nothing. Engineers identify several possible sources of human interference, including a satellite transmission reflected through an unusual path. The direction overlaps the Hesper system within the uncertainty of the first measurement, but not precisely enough to exclude a nearer source. For 4 days, the world waits. The candidate fails verification. The final investigation traces it to a combination of local equipment and a signal from an Earth-orbiting spacecraft. The event is disappointing and scientifically ordinary. Radio astronomy has a long history of signals that appear interesting until interference is understood. The public reaction is not ordinary. Some people refuse the explanation. They claim the signal was suppressed to prevent panic. Others accuse the observatory of manufacturing attention. The scientist whose screenshot leaked receives threats from both sides. The incident leads to stricter procedures for candidate technosignatures. Multiple facilities must confirm a signal. Natural and human sources must be excluded. Data and methods must be released. Communication must distinguish clearly between candidate, verified anomaly, and confirmed technology. The procedures cannot erase emotion. They provide a path through it. Leona is relieved when the signal proves human and surprised by her relief. She wants life elsewhere. She is not certain she wants a message. A microbial biosphere would transform biology. An intelligent civilization would transform every human institution at once. Language, security, philosophy, religion, law, and identity would all confront a mind that developed independently from Earth. The difference between these discoveries is larger than the difference between silence and either one. Pelagos remains quiet. This silence allows the planet to become a cultural surface onto which people project themselves. Novelists imagine cities beneath the clouds. Filmmakers depict oceans filled with transparent giants. Musicians use the planet's 31-hour rotation to compose works that repeat on an unfamiliar day. Architects design buildings for its estimated gravity. Fashion companies produce Pelagos blue, though nobody knows the ocean's actual color. One global art project broadcasts music toward the star despite the communication pause. The transmission is weak compared with the focused message proposals and unlikely to be detectable at the destination. Organizers call it symbolic. Critics ask why symbolic speech still needs a transmitter. The International Communication Council remains divided. After years of discussion, it establishes a rule for government-funded observatories: no deliberate high-power message without broad international review. Private transmitters remain a legal problem. One wealthy entrepreneur constructs a powerful radar facility and announces a personal greeting to Pelagos. The message contains his name, human images, and a statement claiming to represent peaceful Earth. Governments attempt to stop the broadcast through licensing and court orders. The dispute reaches judges who must interpret telecommunications law written for interference on Earth, not speech directed toward another star. The transmitter is disabled before the scheduled date due to a safety violation. The entrepreneur releases the message online and declares censorship. No signal leaves Earth. The incident produces the first international treaty on deliberate interstellar messaging. It does not ban transmission forever. It requires transparent review, scientific assessment, public consultation, and a supermajority of participating states for any message powerful enough to be plausibly detectable. The treaty is imperfect. A determined state or organization could ignore it. It establishes that speaking across interstellar distance is not merely a technical act. It is governance extended through time. Mara studies this debate from a research vessel in the Pacific. She is now an oceanographer examining plankton communities and the gases they exchange with Earth's atmosphere. Pelagos appears in almost every grant proposal she reads, often unnecessarily. Researchers promise that studying Earth oceans will help interpret the distant world. Sometimes the claim is valid. To understand an exoplanet spectrum, astronomers need examples of how living oceans affect atmospheric gases, cloud particles, surface reflection, and seasonal chemistry. Earth is the only inhabited planet available for direct study. Every ecosystem becomes part of the reference library. Mara collects water during a massive plankton bloom. Satellite instruments measure its color from orbit. Atmospheric sensors track gases above it. The campaign asks a simple question: what would this event look like to a telescope 12 light years away? The answer is humbling. Most of the biology disappears into one pale pixel. Under certain conditions, pigments change reflected light slightly. Gases released by microbes alter atmospheric chemistry. Clouds cover much of the evidence. The signal depends on season, viewing angle, and instrument precision. Earth is covered in life. A distant observer could still struggle to prove it. This insight changes the language used for Pelagos. Absence of a clear biosignature cannot prove sterility. Earth itself would have been difficult to identify as inhabited through much of its history. Oxygen became abundant only after life had existed for a very long time. Pelagos may host a biosphere too subtle for current instruments. It may be sterile despite dramatic oxygen. Both possibilities survive. Mara begins collaborating with Leona professionally, something neither expected. The mother provides exoplanet spectra. The daughter provides models of ocean biology, aerosols, and seasonal gases. Their first joint paper examines whether the apparent polar changes on Pelagos could be influenced by biological particles acting as cloud seeds. The conclusion is that the effect is possible and impossible to distinguish from several non-biological mechanisms with current data. Mara laughs when she reads the final sentence. Her mother has spent her career producing increasingly sophisticated ways to say not yet. Leona says not yet is different from no. During the 10th year, a new space telescope begins operating. Its mirror is larger, its starlight suppression more stable, and its instruments designed partly around Pelagos. The first observing campaign lasts 4 months. The improvement is not like changing a blurred photograph into a landscape. It is like turning a few uncertain colors into a moving pattern. Scientists map broad longitudinal regions. They track cloud systems across repeated rotations. They detect a stronger seasonal variation in water vapor and identify trace nitrous oxide at the edge of sensitivity. On Earth, most atmospheric nitrous oxide comes from biology, especially microbial processes, though non-biological pathways exist. The signal is too weak for a claim. Then another molecule appears. Methyl chloride, or something spectrally similar, seems to rise and fall with the same season. No single gas proves life. A collection of gases maintained far from chemical equilibrium, changing in coordinated cycles, can build a stronger case. For the first time, the life hypothesis fits the observations better than every known sterile model. The scientific report does not say life discovered. It assigns probabilities. Under the stated models and assumptions, biological activity is the leading explanation. The number is 72%. News organizations struggle with this. Life is probably there is too strong. Life cannot be ruled out is too weak. 72% sounds precise enough to be trusted and conditional enough to be misunderstood. The public chooses its own language. Pelagos is alive. Leona refuses to say it. Mara does too. In private, they open a bottle of champagne. The first bottle had been waiting in a laboratory refrigerator before the announcement years earlier. This one has been waiting in Leona's home since Mara was 11. They do not toast to confirmed life. They toast to a universe that has become harder to describe as empty. The probability of life changes the probe mission more than the discovery of habitability did. A sterile planet can be studied as geology and climate. A living planet creates obligations. The original Firefly design would pass through the Hesper system at high speed, carrying no fuel for braking. Most probes would observe Pelagos from millions of kilometers away. A small number would pass closer to the atmosphere to analyze gases and photograph the surface. Planetary protection specialists object. At 20% of light speed, even a tiny spacecraft contains enormous kinetic energy. A navigation failure could send a probe into the planet. The chance may be extremely small, but a living world should not receive fragments of Earth electronics and microbes before humanity understands what is there. Engineers respond that the probes can be sterilized and aimed so that their default trajectories miss every planet. Biologists answer that sterilization is never a casual promise. Some Earth organisms survive radiation, vacuum, cold, desiccation, and long dormancy. A probe crossing interstellar space at extreme speed will face harsh conditions, but planetary protection must rely on measured risk rather than assumption. The mission is redesigned. No Firefly is permitted on a collision course with Pelagos. Navigation updates continue through the journey. The closest flybys occur above the atmosphere. Probes that lose communication or control remain on trajectories passing safely outside the system. The change reduces image resolution and atmospheric sampling. It also creates a principle likely to guide every future mission. The first visit should observe the world without becoming one of the events that changes it. A more ambitious proposal suggests building a larger probe able to slow down using a magnetic sail, stellar wind, or a laser system operating from the destination side. None is mature enough for the first mission. The flyby fleet remains the only project with a plausible launch date. Soren Malik becomes the public face of its compromises. He explains repeatedly that the Fireflies will not land, will not collect organisms, and will not send immediate proof of animals, plants, or cities. They may return close images. They may measure atmospheric layers and magnetic fields. They may reveal continents, storms, ice, volcanic plumes, and perhaps pigments at the surface. They will pass the planet in hours after traveling for decades. The mission resembles throwing a camera past an island from a ship that can never turn around. People ask why humanity should build something so limited. Soren answers that the alternative is waiting for technology that may not exist for centuries. The Fireflies are not the final mission. They are the first reduction in distance. The project enters construction during the 15th year after discovery. By then, Pelagos is a permanent part of culture and an inconsistent part of attention. Children learn about it in school. Most adults recognize its name. Scientific updates still make headlines when a new atmospheric molecule appears, but months pass when the planet receives little general coverage. Ordinary life has absorbed extraordinary knowledge. Mara remembers how impossible that seemed on announcement day. She is 26 and leading a research group studying how Earth's ocean color changes across climate cycles. Leona is approaching 60. Tomas, her grandfather, has died. Soren's hair has turned gray. A new generation of engineers enters the Firefly program after growing up with Pelagos as part of ordinary science. One of them is Imani Park, a guidance specialist who was 10 years old when the press conference took place. Her childhood became inseparable from the discovery, though her parents named her after no star or planet. She dislikes when journalists call her a Pelagos child. To Imani, the planet is not a miracle. It is a destination in a requirements document. She spends her days calculating how probes will correct their path after decades of tiny errors. A difference smaller than a degree at launch can become an enormous miss by arrival. The fleet must use stars, pulsars, and the changing position of Hesper 417 to navigate. Earth will continue sending updates, but every command takes longer to arrive as the probes travel outward. Near the destination, instructions from Earth will be more than a decade old by the time they reach the fleet. The machines must make final decisions themselves. Artificial intelligence becomes part of the mission, but not in the form of a conscious explorer. The probes carry systems trained to identify scientific targets, avoid hazards, manage damaged hardware, and prioritize data. Communication capacity will be limited. The fleet may collect far more information than it can transmit across 12 light years. A machine may need to decide whether one image of a coastline is more valuable than 10 measurements of atmospheric chemistry. Scientists debate those priorities for years. Biologists want biosignatures. Geologists want surface composition and tectonic clues. Climate scientists want global weather. SETI researchers want artificial lights, radio sources, unusual heat, and geometry suggesting structures. The public wants a clear photograph. No probe can satisfy every desire during a fast flyby. The final hierarchy places safety and raw measurements first. The probes retain enough unprocessed data to allow future scientists to reinterpret results, but storage and transmission remain finite. Images receive more capacity than some researchers consider rational because images help society understand why the mission matters. Imani argues for another priority. If the probes detect an unexpected signal that could indicate technology, they should change observation plans and coordinate across the fleet. Others worry that an anomaly could distract the mission from broader science. An artificial signal might be interference from probe electronics. A bright geometric feature might be ice or cloud. The compromise resembles the evidence scale developed after the methane crisis. No single anomaly controls the fleet. Several probes must detect compatible evidence before major reallocation occurs. Machines inherit scientific caution. The laser array is constructed in a high desert and in orbit. Ground stations provide much of the power, but Earth's atmosphere limits precision. Orbital mirrors and phased laser platforms combine the beam during launch windows. Energy storage systems release power in controlled bursts. The system becomes one of the largest engineering projects in history. It also becomes a weapon concern. A laser capable of accelerating sails could damage satellites or ground targets if misused. Nations demand monitoring and independent control. No single operator may aim the complete array. Hardware interlocks restrict elevation and target paths. International inspectors observe software and physical systems. Military representatives insist that every powerful technology can have dual use. Critics answer that this is not a reason to build without rules. The Pelagos project creates a model for shared control of planetary-scale infrastructure. Whether the model will survive political crisis remains untested. As launch approaches, people begin asking who will receive the data. The question seems absurd. The information should belong to everyone. Institutions still argue over embargo periods, national investment, patents, and control of communication networks. Companies that build components expect commercial rights to related technology. Governments want priority access in case the probes detect a security threat. The mission charter declares the scientific data a common human archive after basic verification and safety review. Raw signals will be copied across multiple institutions. No government can legally suppress the full dataset. Legal language cannot guarantee courage. It can make secrecy harder. Mara joins the mission's biological advisory panel. Her role is to ensure that ocean and atmospheric interpretations do not assume Pelagos behaves like Earth. At the first meeting, an engineer describes a future image classifier trained on Earth's clouds and coastlines. Mara asks what happens when the planet contains something the classifier has never seen. The engineer says it will choose the nearest category. Mara says the nearest category may be wrong in the most interesting way. The system is changed to preserve uncertainty and flag unfamiliar patterns rather than forcing every observation into an Earth label. Pelagos has spent 15 years teaching humanity the same lesson. Similarity is a starting point. It is not permission to stop looking. The Firefly's launch on the 18th anniversary of the discovery. The date was chosen for orbital geometry rather than symbolism, but the symbolism arrives anyway. Crowds gather near the Desert Laser Complex, though most of the array lies beyond direct view. Public screens show the sail packages in orbit, each folded around a probe smaller than a dinner plate. The probes have already passed years of vacuum, radiation, vibration, and autonomous testing. They do not look like ships. There are no cabins, windows, engines, or flags large enough to see. Each vehicle contains layers of electronics, shielding, instruments, communication surfaces, and a sail packed with impossible precision. The launch sequence will last several days. One group at a time is released into the beam path. The sail unfolds. The laser array locks onto it. For several minutes, light pushes matter. The acceleration is extreme. The first sail tears. Its fragments remain in a monitored orbit and are later collected. Engineers pause the sequence for 9 hours. A manufacturing defect in one edge reinforcement is identified. Every sail from the same batch is removed. The world watches a mission planned for decades stop because of a flaw measured in millimeters. Commentators call the delay embarrassing. Soren calls it the system working. The next sail opens cleanly. The lasers begin. On tracking displays, the probe's velocity climbs far beyond anything humans have launched before. It crosses the distance to the moon in minutes, then continues outward. The beam releases it on a path toward Hesper 417. There is no visible streak across the sky. The launch is represented through numbers. People cheer anyway. Over 4 days, 312 probes enter interstellar trajectories. 7 sails fail deployment. 4 are held back after minor anomalies. 301 depart successfully. They form a long, spreading stream rather than a tight group. Later waves will follow as improved designs become available. The fleet will not coast silently in perfect condition. Interstellar space is thin, not empty. Dust impacts at high speed can erode shielding or destroy a probe. Charged particles damage electronics. Tiny navigation errors accumulate. Some vehicles will fail before reaching the star. The mission expects loss. This is emotionally difficult for a culture taught to think of spacecraft as individual heroes. The Fireflies are designed more like seeds scattered into distance. The mission succeeds if enough survive. Leona watches the launch from the control center with Mara and Imani. Soren stands at the main console. He spent most of his career preparing machines for a moment that lasts minutes. When the final successful probe leaves the beam, the room applauds. Then there is almost nothing to do. The fleet sends status signals while still relatively near Earth. Engineers check orientation, power, clocks, and navigation. Commands can reach the probes quickly by interstellar standards. Within weeks, the communication delay becomes noticeable. Within years, every exchange becomes a conversation with the past. The project changes from launch engineering to long-duration stewardship. Teams monitor the fleet, update software cautiously, refine the target ephemeris, and study failures. New generations of probes are planned with lessons from the first wave. Soren retires 2 years later. At his farewell ceremony, journalists ask whether he regrets never seeing Arrival. He says Arrival was never his part of the mission. His part was making sure there would be something for future people to receive. Imani becomes director of guidance. Mara continues on the Science Council. Leona reduces public work but keeps observing Pelagos through increasingly powerful telescopes. She has spent 18 years looking at the same distant light and has never repeated exactly the same measurement. Clouds change. Seasons return. Atmospheric estimates narrow. Surface maps improve slowly. The 72% life assessment rises and falls as models change. A new geological model produces more non-biological nitrous oxide than expected, reducing confidence. A separate analysis finds that the combination of gases and seasonal variation is difficult to sustain without active chemistry at the surface. The probability reaches 81%, then 68%, then 79%. People complain that science is indecisive. Leona says the planet is not obligated to become easier because humanity gave it a name. The first Firefly failure occurs 4 years into flight. A probe stops transmitting after a period of rising temperature. Another loses attitude control. A third reports a dust impact that destroys one instrument but leaves navigation intact. Each failure receives a short notice. There are no national days of mourning. Engineers still feel the losses personally. They know which hands assembled each probe and which students designed the instruments. A small machine traveling alone through interstellar darkness can become emotionally significant even when hundreds remain. The fleet passes the outer edge of the solar system. The definition of that edge depends on what is being measured. The planets end long before the sun's influence does. The solar wind forms a bubble called the heliosphere, while the sun's gravity extends vastly farther. The Fireflies cross the heliopause into interstellar space within years because of their speed. Voyager took decades to reach that boundary. The comparison becomes part of school lessons. Children track the mission on maps where the solar system occupies a nearly invisible beginning. The distance to Pelagos still dwarfs everything crossed so far. Mara visits a classroom on the 5th mission anniversary. Students ask what the probes can see. Almost nothing useful about the destination yet. They see stars for navigation and measure interstellar dust, magnetic fields, and plasma along the path. This science matters because the region between stars has rarely been sampled directly. The mission produces discoveries before arrival. It maps small-scale structure in the local interstellar medium. Different probes cross slightly different paths and reveal variations in dust and magnetic turbulence. The data improve models of how stellar winds interact and how interstellar material enters the solar system. The planet gave humanity a reason to build the fleet. The journey becomes a field of science on its own. One student asks whether Pelagos might disappear before the probes arrive. The planet will not vanish in any ordinary sense. Its observed conditions could change. A massive volcanic event, impact, climate shift, or technological transformation might occur during the 60-year journey. The probes are traveling toward a world different from the one that inspired launch. This is true of every long journey. It is usually less visible. The light reaching Earth during the mission continues, showing Pelagos 12 years in the past. The probes themselves are also moving through delayed knowledge. Course updates use newer observations, but the fleet can never know the destination's exact present until it arrives. Interstellar exploration is pursuit of a moving past. The communication treaty faces a new challenge when the Fireflies pass beyond the solar system. Should the probes carry a message? Their primary transmissions point back toward Earth, but they possess low-power systems that could broadcast locally near Pelagos. The original mission design included a mathematical identification packet in case artificial receivers detect them. The packet states that the probes are from the solar system and are intended for observation. Critics say even this is unauthorized contact. Engineers say a machine entering another system should identify itself if intelligence exists there. Others warn that a message designed decades earlier may become politically outdated before arrival. The mission charter requires review every 10 years. Future generations may update the packet while communication with the fleet remains possible. This creates an unusual democratic responsibility. People who did not approve the launch can still alter what the probes say. People who launched them cannot control the final choice. At the first review, the packet remains. A single sentence is added in mathematical encoding. We do not know whether anyone is there. It is the most honest greeting the mission can offer. 48 years after the announcement, Pelagos is no longer the only confirmed habitable planet. Improved surveys identify 4 more worlds meeting the same broad standard, though each is farther away or less favorable for study. One orbits a red dwarf and may be tidally locked. Another is larger than Earth, with a deep atmosphere and a global ocean. A third has broad seasonal ice and uncertain surface pressure. The fourth circles a sun-like star 87 light-years away. The first discovery made habitability real. The later discoveries make it statistical. Pelagos remains special because it is near, well-observed, and tied to a generation's memory. It no longer carries the burden of representing every possible living world. This is scientifically healthy. Planets turn out to be diverse in ways one example could never reveal. Habitable does not describe one Earth template repeated through the galaxy. It describes a range of conditions in which liquid water and complex chemistry can persist. Some worlds have long days. Some orbit double stars. Some may contain deep oceans with little exposed land. Some experience stronger seasons or thicker clouds. A habitable planet around a red dwarf may keep one side facing its star, yet atmospheric and ocean circulation could transport heat into the dark hemisphere. The boundary between permanent day and night may not be the only mild region. Models show many possibilities depending on pressure, oceans, clouds, and the star's activity. The phrase another Earth becomes less useful with every discovery. The galaxy appears to contain other homes for life, not copies of human home. This changes the Drake equation, the famous framework used to organize uncertainties about communicating civilizations. One term concerns the fraction of stars with planets. Another concerns how many planets could support life. Exoplanet surveys make those terms less uncertain. The hardest terms remain. How often does life begin? How often does it become complex? How often does intelligence produce detectable technology? How long does a technological civilization remain detectable? Pelagos improves one part of the equation and leaves the deepest questions untouched. The lack of a signal becomes more interesting but not conclusive. SETI searches several habitable planets and detects no confirmed technology. The silence could mean intelligence is rare, technology is quiet, civilizations are brief, signals are difficult to recognize, or the search remains small compared with the galaxy. A library cannot be declared empty after checking 5 shelves. Public fascination shifts from whether habitable worlds exist to whether any are alive. Pelagos remains the strongest candidate. A new generation of telescopes resolves surface reflection at finer scales. One recurring region absorbs light in a pattern unlike most known minerals. The signal shifts seasonally and follows rainfall predicted by climate models. Researchers compare it with Earth's vegetation red edge, a sharp change in how plants reflect near-infrared light. The Pelagos feature appears at different wavelengths, as expected under an orange star. The result receives the cautious name surface pigment candidate. It could represent photosynthetic organisms. It could represent minerals, chemical films, or an interaction of clouds and surface water. Laboratories begin creating pigments optimized for the star's spectrum. Dark purple and near-black microbial mats perform well in simulations. Artists feel vindicated. Scientists remind them that plausibility is not observation. Mara is 59 when she helps publish the analysis. Leona is 88. They sit together during the press briefing, mother and daughter linked to the planet through different disciplines. Leona's voice is softer than it was on announcement day. Mara now gives most of the answers. A journalist asks whether they finally believe Pelagos is alive. Leona says belief is not the category she would use. Mara says the living world hypothesis explains more observations with fewer special assumptions than it did decades earlier. The journalist asks whether that means yes. Mara says it means the evidence is becoming difficult to explain without biology. The public calls this confirmation. Scientific bodies do not. The disagreement is smaller than before because people have learned the language of accumulated evidence. School children know that a biosignature is not one magical molecule. It is a pattern tested against geology, atmospheric chemistry, stellar radiation, climate, and time. Pelagos becomes the first planet widely treated as probably inhabited while remaining officially unconfirmed. This intermediate status lasts for decades. It influences art, ethics, and law as though life were present, because waiting for absolute certainty before protection could become a decision to risk harm. Future mission plans adopt life-positive precautions. Any orbiter or lander must assume biology exists until evidence shows otherwise. Sterilization standards become stricter. Impact probabilities approach zero. Sample return proposals are postponed until containment methods can address chemistry and biology with no shared evolutionary history. Some critics say protecting hypothetical microbes is irrational. Biologists answer that the cost of caution is delay, while the cost of contamination could be permanent confusion or damage. If Earth organisms reached Pelagos and survived, future scientists might never know which biology originated there. If Pelagos organisms reached Earth, most might find human chemistry useless. Some could produce unexpected reactions. Shared water and carbon do not guarantee compatibility or danger. The honest answer is uncertainty in both directions. Planetary protection becomes an ethic of preserving the possibility of knowledge. Mara's own daughter, Lena, joins the Firefly data team. Lena was born after launch and grew up receiving status reports from probes older than she was. She becomes an optical communications engineer responsible for finding signals that will eventually be weaker than background noise. The fleet is halfway to Hesper 417 when she begins. Signals from individual probes are faint. Ground and space receivers combine observations. Error-correcting codes reconstruct messages from missing fragments. The probes transmit slowly to conserve energy and maintain reliability. A family photograph can move across Earth in seconds. A technical report from a Firefly may take days to assemble. Lena learns patience through packets. She also learns that the mission archive contains voices from the dead. Soren recorded design explanations before retirement. Tomas Reyes contributed a classroom message included in the educational archive. Engineers who died years earlier appear in training videos, describing choices whose consequences remain in flight. A multi-generational project creates a strange community across time. The living maintain machines designed by the dead for recipients not yet born. Leona visits the communication center once. A status signal from probe 146 is being decoded. The message began its journey years earlier from a point between the stars. It reports that the probe is healthy and has corrected its course by an angle too small for Leona to imagine visually. She places a hand on Lena's shoulder. 3 generations of the family have now worked on different sides of one distant world. Leona asks whether Lena expects to see arrival. If the schedule holds, Lena will be in her 70s when the first close data return. She says yes. Leona smiles at the confidence. The mission has always depended on people believing they will be present for futures nobody can guarantee. Leona dies 2 years later. Her final scientific paper does not concern oxygen, pigments, or life. It concerns uncertainty labels in public planetary maps. She argues that every future image should show which details are measured, modeled, inferred, or imagined. After a career spent turning light into worlds, she wants the boundary to remain visible. At her memorial, Mara does not describe her mother as the person who discovered Pelagos. Thousands of people contributed. She says Leona was one of the people who taught humanity how not to claim more than the light had said. The first announcement plays briefly. The wording is still careful. A rocky world with stable surface temperatures, a substantial atmosphere, and persistent liquid water. Half a century later, every part of it remains true. The unanswered question remains alive. The Fireflies reached the Hesper system 63 years after launch. Earth does not learn this immediately. At the moment the first probe crosses the outer system, the news is still 12.3 years away. Probe 084 detects the change first. The star is no longer a point used for navigation. It is a sun filling a significant part of the forward sensors. Dust density rises. Magnetic fields change. The probe begins the arrival sequence written by engineers across several generations. Other surviving probes respond. Of the 301 launched in the first wave, 187 still transmit. Some lost instruments. Some operate with reduced power. Later waves are years behind. The fleet spreads into observation paths around the system. Several probes target the outer planets and debris belts. Most focus on Pelagos. No human being watches in real time. The machines coordinate through local light speed communication measured in minutes rather than years. They compare navigation, detect hazards, and vote on unexpected observations according to rules amended throughout the journey. The star has 5 known planets. The Fireflies discover a 6th. It is a small frozen world beyond the previous detection limit. The finding would have dominated astronomy in another system. Here, it becomes part of a crowded arrival archive. Pelagos appears first as a crescent. The closest probes are still millions of kilometers away, but the planet is no longer blended into a few remote pixels. Oceans reflect the star. Cloud systems curl across the atmosphere. A polar cap covers part of the north. 2 large land masses cross the illuminated side. The color is not earth blue. The ocean appears darker, almost slate beneath the orange star. Land ranges from brown to charcoal with broad regions showing a deep violet-black reflectance. The surface pigment candidate is real. That still does not prove life. Minerals can be dark. Chemical coatings can spread across wet rock. The probes begin spectroscopy at resolutions impossible from Earth. They find repeated absorption features matching complex organic pigments. They detect oxygen, methane, nitrous oxide, and several sulfur compounds arranged across seasons and geography in patterns no known sterile model predicts well. The atmosphere is chemically active. Probe 203 photographs long streaks in a coastal ocean. The streaks shift across consecutive rotations and correspond with changes in reflected light, as plankton blooms do on Earth. The evidence passes the fleet's biological threshold. Life becomes the leading explanation with overwhelming confidence. The probes do not announce this to anyone. They begin transmitting. The message is divided across many vehicles and repeated through different channels. Highest priority packets contain instrument calibration, raw atmospheric spectra, navigation, and context. Images follow. The fleet knows that several probes may fail before their signals cross the distance. For 12 years, the proof travels through darkness. On Earth, the Pelagos mission has become an inheritance more than a news story. The arrival date is known, but there is no exact day when the first message should appear. Probe speeds and routes differ. Communication systems may need time to acquire Earth. Receivers monitor continuously. Lena Park Reyes is in her 70s. She directs the network that has spent years rehearsing arrival. She is Mara's daughter and Leona's granddaughter, though professional biographies mention this more often than she does. Mara is 104 and lives near the coast. Her health no longer allows regular travel. She follows mission reports through a screen positioned beside a window overlooking Earth's Pacific. The first signal does not arrive as a picture. It appears as a pattern in noise at 3:18 in the morning. A receiver in lunar orbit identifies the expected code. Ground stations in Australia and Chile confirm it. The signal is too incomplete to interpret, but its timing and frequency match probe 084. An automated message wakes Lena. She has imagined this moment since childhood. She arrives at the communications center and discovers that the data are not ready. Engineers need hours to combine fragments. There is no dramatic sentence waiting on the screen. There are packets, checksums, missing blocks, and calibration tables. The first verified result is the position of the probe. It reached the system. The second is the number of responding fireflies. The third is a spectrum of pelagos. Scientists recognize the gases before the full pipeline finishes. Lena calls Mara. Her mother does not ask for probabilities. She asks whether there is an ocean. Lena says yes. The first image is released to the scientific team under the mission charter's short verification period. It shows a crescent world crossed by cloud and dark sea. The image is sharper than any reconstruction and less detailed than generations of paintings. No forests are visible. No animals appear. No cities glow. It is simply a planet. Mara looks at it for several minutes. She says the clouds are in the wrong places. Lena asks wrong compared with what? Mara says compared with the picture she carried for more than 90 years. The biological evidence requires 2 more days of review. Independent teams check calibration. They compare signals from multiple probes. They test mineral, photochemical, and volcanic alternatives. The conclusion is stronger than any remote observation could provide. Pelagos contains a global process producing complex organic pigments and maintaining atmospheric gases far from chemical equilibrium. The ocean streaks change in ways consistent with widespread photosynthetic microorganisms or an alien process performing a similar ecological role. The announcement is made at the same conference hall where Leona spoke nearly a century earlier. The building has been renovated, but the stage remains. Lena stands at the lectern. She does not say that intelligent life has been found. She does not say plants. She does not say humans can live there. She says that multiple independent measurements from the Firefly fleet provide compelling evidence of a planetary biosphere. This time, the room stays quiet longer. Humanity has found life beyond Earth. The discovery answers one ancient question and opens thousands more. Either life began independently at least twice, or it moved between worlds through rocks, dust, or some older process no one yet understands. If Pelagos biology uses DNA, the same genetic code, and familiar cell chemistry, scientists must ask whether the 2 biospheres share ancestry. If it uses entirely different molecules, then life may emerge through more than one path. The Fireflies cannot answer every question. They have no landers and no sample laboratories. They can map pigments, gases, climate, and broad surface activity. The close flybys reveal no obvious technosignatures. There are no patterned night lights, narrow radio emissions, industrial gases, or structures large enough to distinguish. The absence does not prove intelligence has never existed or exists nowhere. The visible biosphere appears microbial or simple at planetary scale. This is enough. On Earth, celebrations begin before the press conference ends. Religious communities, laboratories, schools, streets, and homes respond in different ways. Some people cry. Some are frightened. Some feel smaller. Others feel less alone. Most go to work the next day. The extraordinary enters ordinary life again. Mara does not attend the public celebration. She sits beside the ocean and listens to waves from the only living planet she has ever touched. Pelagos is no longer only habitable. It is inhabited. The distance between those words took more than 90 years to cross. Confirmation of life does not make Pelagos easier to reach. It makes reaching it more ethically complicated. Within hours of the announcement, proposals appear for orbiters, atmospheric probes, landers, submarines, sample collection, and eventual human settlement. Many use technology that does not yet exist. Several assume that a living world is more valuable if humans can touch it. Biologists urge restraint. The fireflies have revealed enough to show that Pelagos is not an empty laboratory. Its oceans contain a planetary process changing atmosphere and light. Any descent must be designed around a biosphere whose chemistry, ecology, and vulnerability remain unknown. A lander sterilized by Earth standards may still carry molecules or organisms able to interfere. A probe entering the ocean could damage a community or confuse future measurements. A sample returned to Earth could contain harmless chemistry, toxic compounds, self-replicating systems, or nothing capable of functioning outside Pelagos. Nobody knows. The old planetary protection rules were created for Mars, icy moons, and solar system bodies close enough for repeated missions. Pelagos requires decisions spanning centuries. The first international agreement after confirmation is called the Pelagos Biosphere Accord. It establishes a presumption against contact. Remote observation may continue. Flybys and distant orbiters are allowed under strict non-impact rules. Any atmospheric entry requires evidence that contamination risk is negligible and scientific value cannot be obtained from outside. No sample may return to Earth until containment systems can address non-Earth biology without assuming familiar genetics or metabolism. Human settlement is excluded from international mission planning. The Accord has no power over every future government. It creates a moral baseline. Some critics accuse humanity of discovering the first alien life and immediately placing it behind glass. They argue that exploration always carries risk and that knowledge cannot advance through permanent distance. Others say the discovery is important precisely because Pelagos has a history unrelated to human needs. The first independent biosphere should not become a colony before it becomes understood. The debate introduces a new idea into law. Does a biosphere possess value even when no intelligent beings can claim rights? Earth laws protect species, habitats, and ecological systems, but usually through human governments and interests. Pelagos has no representative able to attend negotiations. Scientists, ethicists, indigenous scholars, legal experts, and religious thinkers propose different frameworks. Some speak of guardianship. Some speak of the rights of living systems. Others resist granting legal personhood to a planet observed only through machines. The agreement settles on duty rather than rights. Humanity has a duty not to cause irreversible harm where knowledge is incomplete and no consent is possible. This principle affects Earth too. Arguments used for Pelagos protection return to forests, reefs, rivers, and deep oceans. If an alien microbial mat deserves caution because it represents a unique evolutionary history, so does an Earth ecosystem containing branches of life found nowhere else. The distant planet does not suddenly end environmental destruction. It makes some excuses sound thinner. Biology experiences a revolution before any alien cell is examined directly. Pelagos proves that life can emerge or survive on another world. Researchers compare the planetary spectrum with Earth's history. They model possible pigments, membranes, energy pathways, and atmospheric cycles. The dark surface regions absorb the orange star's available light efficiently. If they are photosynthetic, their pigments may use different molecular structures from chlorophyll. The coastal blooms may consist of cells, films, floating colonies, or organisms beyond Earth's categories. Scientists avoid naming species from pixels. Popular culture does not. Children's books fill the oceans with Pelagians. Toys glow purple. An animated film gives the microbes faces. The biological reality remains inaccessible and changes science anyway. The probability that life begins readily under suitable conditions rises. Estimates of living worlds across the galaxy expand. Searches target atmospheric disequilibrium, surface pigments, and seasonal changes on other planets. As the broader search improves, 2 more worlds begin showing weaker possible biosignatures. Pelagos is no longer evidence that one other biosphere exists. It may be the first member of a population. The discovery of microbial life does not solve the silence of intelligence. If simple life is common and technology remains undetected, then the path from chemistry to civilization may be rare, slow, fragile, or quiet. Earth spent most of its living history without animals and nearly all of it without radio. A universe rich in microbes can still feel silent across technological distance. SETI searches Pelagos more deeply after the fireflies arrive. Close observations identify natural radio emissions from lightning and the planet's magnetic environment. No artificial signal appears. The communication packet carried by the probes receives no answer. This creates relief and disappointment. Intelligent life might have required a different chapter of Pelagos' history. It might exist beneath ocean or cloud without detectable industry. It might use communication humanity cannot recognize. Or it may never have developed. Habitability was never a promise of conversation. Lena directs the Arrival archive for 8 years. The fireflies continue transmitting as long as their power survives. Probes on different paths photograph the changing planet. One captures a large storm crossing an ocean. Another observes a volcanic plume rising from a landmass near the equator. Several detect auroras around the poles, confirming a magnetic field strong enough to shape incoming particles. A probe looking back during departure photographs Pelagos as a full disk beside its orange star. That image becomes the most reproduced picture in history after Earth from space. The planet is small, clouded, and clearly separate from home. Mara sees the image before she dies at 106. Lena visits with a printed copy. Her mother traces the bright edge of the northern ice and the dark curve of ocean. Mara spent her career explaining that an alien ocean might not behave like Earth's. Now she can see waves only as patterns of reflected light. She says the distance still feels honest. Lena asks what that means. Mara says Pelagos gave humanity knowledge without pretending to belong to humanity. At her memorial, Lena returns to the first image released on announcement day. The reconstruction is beautiful and wrong in countless details. Continents lie in different places. Clouds have the wrong structure. The ocean is too blue. The polar ice is too symmetrical. The image was not useless. It carried people across 90 years of waiting. Science advances by replacing useful pictures with less wrong ones. The next mission is approved after decades of debate. It is not a lander. It is a large observatory designed to decelerate into the Hesper system using a combination of magnetic sail and stellar light maneuvering. Travel will take longer than the fireflies. Once there, it can remain for years, map the planet continuously, and deploy sterile atmospheric balloons only if later review permits. The mission is named Leona, not after one person alone, but after the old word associated with light and the generations who learned to read it carefully. Lena objects to the name and loses the vote. Construction begins after her retirement. She knows she will not see Arrival. The pattern repeats. Every generation receives an unfinished world from the generation before it and leaves a more detailed question for the next. This is the practical meaning of finding Pelagos tomorrow. The announcement would be immediate. Understanding would be inherited. A child could grow old while the planet remained a few pixels. A probe could spend a human lifetime crossing the darkness. Proof of life could arrive after the people who first hoped for it were gone. The discovery would not compress the universe into human speed. It would invite human institutions to become patient enough for the universe. What, then, would actually happen if humanity found a habitable planet tomorrow? The first answer is that the word found would require explanation. Astronomers would not discover a blue world during breakfast and know everything by lunch. A responsible announcement would follow years of measurements, independent verification, and arguments about instruments and models. The news could break tomorrow. The evidence would have begun accumulating long before. The second answer is that habitable would be narrower than the public first imagines. A planet in the habitable zone receives an amount of starlight compatible with surface liquid water under a suitable atmosphere. That is a useful starting point, not a complete diagnosis. Venus and Mars show why orbit is not enough. Atmospheric pressure, greenhouse gases, clouds, magnetic environment, geology, rotation, water history, and the behavior of the star all shape whether a planet can maintain mild conditions. To call the world confirmed habitable in the strong sense used in this story, scientists would need evidence of a rocky planet, a stable atmosphere, suitable temperatures, and persistent liquid water. Even then, a human could not assume the air is safe. Breathable oxygen concentration would need to be measured. Trace gases could be toxic. Pressure and climate could vary. Radiation, dust, and local chemistry would matter. If alien organisms exist, biological interaction would be unknown. Habitable for life is not cleared for human arrival. The third answer is that habitability would not prove life. Water, carbon dioxide, clouds, and oxygen can arise without biology. Oxygen is especially tempting because Earth's atmosphere is rich in it through photosynthesis, yet non-living processes can also produce oxygen under some planetary conditions. Scientists would search for context. What kind of star does the planet orbit? How much ultraviolet radiation reaches it? Are carbon monoxide or other gases present in combinations suggesting non-biological oxygen? Does methane coexist with oxygen? Do gases change seasonally? Does the surface show pigments or patterns connected to climate? No single biosignature should carry the entire claim. The strongest case would come from multiple independent observations that biology explains better than known geology and chemistry. Even then, discovery of life might arrive first as confidence rather than certainty. The fourth answer is distance. A nearby exoplanet can still be unimaginably far from human travel. Proxima Centauri, the closest star beyond the Sun, is more than 4 light-years away. Light reaches it in more than 4 years. Present spacecraft would require thousands or tens of thousands of years to cover similar distances. Our imagined Pelagos lies 12.3 light-years away. That is close enough for detailed astronomy and too far for ordinary spaceflight. A radio message requires 12.3 years to arrive. A reply requires at least another 12.3. A probe traveling at a remarkable fraction of light speed still needs decades. The discovery would therefore affect the mind much sooner than the body. People could know the planet exists. Almost nobody alive at the announcement would ever approach it. The fifth answer is that Earth would not receive a practical replacement. No climate crisis, war, or resource shortage could be solved by moving billions of people across light years. Even if future physics and engineering produced far faster spacecraft, transporting a civilization would be harder than protecting the environment already supporting it. Pelagos might inspire long-term settlement dreams. It would strengthen the immediate fact that Earth is the only habitable world available to present humanity. A second known ocean does not make Earth's ocean less necessary. The sixth answer is that science and funding would change rapidly. Astronomy, planetary climate science, atmospheric chemistry, astrobiology, telescope engineering, and propulsion research would receive new attention. Existing missions would be redirected where possible. New instruments would be designed around the target. Students would enter relevant fields. Companies would pursue both useful technology and empty marketing. Governments would cooperate, compete, and do both at once. The discovery would accelerate tools whose benefits extend beyond the planet. Better imaging, sensors, autonomous systems, power, communication, and Earth observation methods. It would also draw resources away from other work unless budgets expanded. Scientific importance does not remove choices about priority. The seventh answer is that public reaction would be enormous and temporary. For days or weeks, pelagos would dominate conversation. People would feel wonder, fear, hope, skepticism, and cosmic relief. Religious and philosophical traditions would respond in varied ways rather than one global crisis. Misinformation would spread beside real data. False pictures would show forests and cities. Scams would sell land no law can own. Conspiracy theories would claim secret contact. Then ordinary life would return. The planet would remain historically important while no longer occupying every morning. This is how human attention absorbs even extraordinary facts. The eighth answer is that communication would become a political question before it became a conversation. Listening creates little direct risk. Sending a focused message makes a decision for future generations and for people who did not consent. Who speaks for Earth? What should a message contain? Should humanity wait for evidence of intelligence? Could silence be more responsible than greeting? There is no existing authority accepted by everyone. A discovery tomorrow would force international institutions to create procedures while private actors tested the limits. Any answer from 12 light years away would arrive decades after the first choice. Interstellar communication is diplomacy with the future. The ninth answer is that a probe would be possible in principle before a human mission. Tiny laser-driven sails might someday reach a substantial fraction of light speed, though the required power, materials, navigation, survival, and communication remain enormous engineering challenges. Larger crewed ships would be far more difficult. A robotic flyby could become the first realistic physical response to the discovery. Its builders might never see a rival. Its data could belong to their grandchildren. The mission would demand institutions capable of preserving knowledge, funding, and purpose across generations. Humanity has completed long projects before. Few have required the machine itself to cross the years between designers and recipients. The 10th answer is that a living planet would require restraint. The closer humanity comes, the more important contamination becomes. Earth organisms should not be allowed to reach an alien biosphere accidentally. Alien material should not return without containment and understanding. The first mission might need to remain distant. The first landing might be delayed. A planet can be scientifically priceless precisely because no human footprint exists there. Exploration does not always mean touching. Sometimes it means building instruments good enough to leave the object unchanged. The final answer is that discovering a habitable planet would change humanity profoundly without changing most human days. People would still make breakfast, miss trains, care for children, pay bills, fall in love, become ill, and sleep. The planet would exist behind those activities as a new fact. There is another ocean under another sky. There may be another biology. Earth is not the only place where mild planetary conditions can appear. This knowledge would make the universe feel less empty and more demanding. Less empty because one of the possibilities imagined for centuries had become real. More demanding because another habitable world would not answer what humanity should do with its own. Pelagos would not rescue us. It would enlarge the world in which responsibility exists. To let that answer settle, return now to the night after the announcement, when Leona comes home long after Mara should have been asleep. The apartment is dark except for the kitchen light. Tomas has gone home. Mara is sitting at the table with the printed spectrum in front of her. She has colored the water lines blue, the oxygen lines green, and the carbon dioxide lines orange. The colors are not scientifically meaningful. They make the graph easier to hold in the mind. Leona takes off her shoes and sits beside her. For several minutes, neither speaks. The day has contained cameras, questions, corrections, congratulations, arguments, and messages from people Leona has not heard from in 20 years. She has repeated the same careful sentences until they no longer feel connected to the planet. Mara asks whether they can see Pelagos from the roof. Leona says no. They go anyway. The city is brighter than usual. People have gathered in courtyards, parks, balconies, and streets. Amateur telescopes point toward the wrong part of the sky because the Hesper system is not visible at this hour from their location. Nobody appears discouraged. The discovery has given people a reason to look up even when the target is below the horizon. Leona and Mara climb the final stairs and step into the night air. The roof is nearly empty. A neighbor stands near the edge holding binoculars. An airplane crosses between stars. Mara asks which direction Pelagos is in. Leona points toward a section of sky hidden by a building. That seems unfair. A planet can reshape the world's imagination and remain behind an apartment wall. They sit on the warm roof surface. Mara asks the question she has been saving. Do you think something is alive there? Leona has answered this publicly with evidence and caution. She answers her daughter differently. I think it is possible enough to keep looking. Mara asks whether that is what hope means. Leona says scientific hope should be willing to lose. It should survive the possibility that the answer is no. Mara considers this and says it sounds like a bad kind of hope. Leona agrees that it is difficult. Years later, Mara will remember the conversation differently. She will remember her mother saying that hope must be patient. Leona will remember saying nothing so elegant. Memory improves sentences the way illustrations improve planets. The real moment remains quieter. A breeze crosses the roof. Somewhere below, a television repeats the press conference. Leona hears her own voice through an open window, delayed by a few seconds and flattened by speakers. A rocky planet with stable surface temperatures, a substantial atmosphere, and persistent liquid water. The words drift upward into the night. At Pelagos, nothing hears them. The planet is 12.3 light-years away. The announcement has barely begun leaving Earth. Its radio waves expand outward at the speed of light, crossing the solar system, then the space between stars. If technology exists on Pelagos, and if receivers point toward Earth, the news that humanity has discovered the planet will not arrive there for more than 12 years. The humans on the roof are reacting to light that left Pelagos when Mara was not yet born. Two worlds have entered a relationship made entirely from delay. One observes. The other does not know it is observed. This is not unusual in astronomy. Every star is seen in the past. The moon appears as it was a little more than a second ago. The sun appears as it was about 8 minutes ago. Nearby stars appear years ago. Distant galaxies appear millions or billions of years in the past. The night sky is not a picture of one universal present. It is an archive arranged by distance. Pelagos changes that familiar fact emotionally. The delayed light now belongs to a place where rain may fall, clouds may gather, ice may melt, and perhaps living chemistry may respond to an orange sunrise. The past is no longer only stars. It may contain weather. It may contain life. Leona lies back against the roof. Mara does the same. They cannot see the planet. They can see the darkness its light has crossed. Imagine following one small portion of that light backward. Leave the city roof. Past the upper atmosphere, where air thins and the blue of day would fade into black. Cross the orbit of the moon. Move beyond Mars, the asteroid belt, Jupiter, Saturn, Uranus, and Neptune. Past the region where the solar wind weakens and interstellar space begins. The sun shrinks into another star. Years pass in distance rather than time. Other stars shift slowly across the field. Dust grains move through darkness. Magnetic fields curve invisibly. No road marks the direction. No sign says that an ocean lies ahead. Then Hesper 417 grows brighter. It is smaller and cooler than the sun, with warmer colored light. Planets move around it according to gravity, unaware of human categories. One of them is Pelagos. Approach from far above its orbital plane. The planet begins as a point and becomes a disk. Clouds appear first, pale across the darker surface. An ocean reflects a narrow path of starlight. Land turns beneath the atmosphere. Ice brightens one pole. No artist has chosen these colors. No public vote has named the continents. No spacecraft has touched the air. The planet does not resemble Earth from every angle. Its days are longer. Its year is shorter. Its star changes the color of noon. Its oceans and atmosphere have histories no human being has lived. It remains habitable without becoming familiar. Perhaps nothing moves in its water except currents. Perhaps microbial films cover coastlines. Perhaps photosynthetic cells darken broad shallow seas. Perhaps life is present beneath the surface and almost invisible from space. The planet does not reveal the answer tonight. That is not a failure of the story. The discovery tomorrow would be the beginning of a longer question, not the sudden end of one. The first morning would tell humanity that another suitable world exists. The following years would teach how hard it is to distinguish possibility from life. The following decades would turn instruments toward faint gases and changing colors. The following generations might send machines into the distance. Every answer would arrive carrying more questions. This is how the frontier would move, not through one announcement from mystery to certainty, but through a series of smaller crossings. Candidate to planet. Planet to rocky world. Rocky world to ocean world. Ocean world to habitable world. Habitable world, perhaps, to living world. Each step would require evidence, patience, and the courage to correct the picture created at the step before. For tonight, the first step is enough. Somewhere beyond the reach of ordinary sight, a world circles another star. In our thought experiment, its oceans are real. Its clouds are real. The water moving through its atmosphere is not an artist's decoration. It falls, gathers, evaporates, and returns. The planet has been doing this without an audience for longer than human beings have existed. Discovery does not begin its story. Discovery begins ours. Back on the roof, Mara asks whether her mother thinks humans will ever go there. Leona says she does not know. Mara asks whether that makes the discovery sad. Leona says no. A place does not have to be reachable to be meaningful. Most of the universe will never be touched by human hands. Knowledge can still connect a mind to it. Care can exist without ownership. Wonder can exist without arrival. Mara is quiet. Below them, the city begins returning to its ordinary night. Televisions switch off. People leave balconies. Telescopes are carried downstairs. Children are reminded that school still opens in the morning. The planet remains. It will remain when the headlines change. It will remain while instruments are designed, careers begin, and generations grow older. It will remain while a probe crosses darkness one small fraction at a time. It will remain after the people who named it are gone. This endurance does not make human attention unimportant. It makes attention a visitor. Tonight, you can let your own attention visit for a little longer. Imagine the pale curve of cloud, the dark ocean beneath it, the slow rotation carrying one coast into night and another toward morning. No city needs to be there. No signal needs to arrive. No intelligent eyes need to look back for the world to matter. A habitable planet would be extraordinary before life was confirmed because it would show that Earth's broad physical possibility is not unique. A living planet would be more extraordinary still, but the quietest wonder may be simpler. The universe can contain real places beyond every life you will personally live. Places with weather you will never feel. Horizons no human eye will see. Days that pass without entering any human calendar. The knowledge does not reduce your own life. It places it inside something larger. The bed beneath you is on one planet. The air around you belongs to one atmosphere. The water inside your body has moved through clouds, rivers, oceans, organisms, and stone on Earth. This world is not abstract to you. It supports your weight. It provides the oxygen entering with each breath. It holds every person you have known and every ordinary task waiting for another day. Pelagos would not replace that intimacy. It would clarify it. A distant world may be habitable. Earth is inhabited by your life. The difference is personal. So let the imagined press conference fade now. Let the cameras switch off. Let the headlines become quiet. The scientists can continue checking spectra without you. Telescopes can keep collecting light. Computers can compare models. Engineers can design patient machines for journeys longer than careers. Nothing in that work requires your attention before morning. The light from Pelagos has already traveled for more than 12 years. It will not arrive faster because you remain awake. The planet will complete its orbit without being watched. Clouds will cross its ocean. A season will change somewhere beneath its orange star. Here, on Earth, the room around you can become smaller and calmer. The great distances do not need to be crossed tonight. The ancient questions do not need to be settled. Your breathing can remain close. Your body can become heavier against the surface holding it. Thoughts can lose their need to reach a conclusion. Imagine the city roof one final time. Leona and Mara have gone downstairs. The warm concrete is empty. Above it, familiar stars remain in their delayed places. Behind one building, too faint to see, lies the direction of Hesper 417. Nothing announces it. No line connects Earth to the planet. Only light crosses the space between them. Patiently, silently, without becoming tired. You do not need to follow it farther. Let the distant ocean remain beneath its unseen clouds. Let tomorrow keep the discovery until tomorrow. And let this planet, the one already beneath you, carry you gently through the night. Sleep well.